All right, I think we're about ready for the session to begin. Please take a seat. By the way, if you're the speaker for the Taking Back Control talk, if you could come toward the front. I haven't seen you yet, so you'll be speaking next. So I would like to make sure that you're present. Okay, so let's begin. This is the formal methods in compilation and implementation session. In my experience, if this session has an "and" in the title, that means there's going to be a wide variety of talks, and that is indeed in store for us in this session. So first we have Dan Leijen, and he's going to be telling us about how you can generalize tail-recursion modulo cons to tail-recursion modulo contexts. So let's welcome Dan.
Working? Yes. Thank you so much, everyone, for coming. Really appreciate it. So I'm Daan, and this is really joint work with Anton Lorenzen, amazing guy. He's at the University of Edinburgh. And we worked on tail-recursion modulo context, an equational approach. And it's a bit unusual for POPL because it's both beautiful and elegant, but also quite useful, I think. I hope you'll enjoy it. So actually, unfortunately, the paper is quite dense, but I tried, like in this talk, to make it more concrete and give the intuition behind everything. So let's dive in. So here's like functional programming, length of a list, like perfect. This is in Koka. It's a strict language. And of course, when you look at it, you're like, it's not so great because it's strict, and we use text-based linear in the length of the list. The length call is not quite a tail call. There's still something to be done later on, like there's a context that needs to be done. So we can't make it a tail call. But of course, we're all functional programmers, so we know how to make it tail-recursive. Right? You can write the tail-recursive version by kind of doing the increment up front and using some accumulating parameter. And there's many examples of this, like maybe reversing a list. Again, it's not quite tail-recursive, which would be very efficient. No, there's still something to be done after the recursive call. And again, as functional programmers, we know how to make this tail-recursive. And now, we will do like a append later on, and again, we have this accumulating parameter. But here you already see something weird is happening. First, I was appending on the right, now I'm appending on the left. What's up with that, right? So, of course, you don't really want to write this all the time by hand in all your library functions. So, we actually have now an algorithm, and that's described in our paper, and it will automatically take these functions that you write in the obvious functional way and reliably generate these tail-recursive functions. And the algorithm, I'm going to give the intuition behind it. It just needs 4 ingredients. So first, you're going to tell the algorithm, the general algorithm, well, what kind of context can we handle? And you would have different instantiations for all kinds of contexts. So for example, here, it would be like right-biased appends. That would be a context. And our algorithm will take all matches of that with recursive calls and generate kind of the same kind of pattern where we compose a accumulating parameter. So then you have to give, as a compiler writer, 3 operations. You have to kind of define in the compiler how you can take a context and convert it in your abstract accumulating context. And you have to give a little function that says how you compose 2 of these abstract contexts, and the function that says how you apply it in the end to the final result. And those are the 4 things you need to instantiate the generic algorithm. And there's many examples of this. So I'll give a concrete example with length. So let's look at length. So first you would, in the compiler, you would say, I want to optimize these functions. So you would define like left-biased integer addition, for example. And then the algorithm will already run and generate this pattern where an abstract context is composed with concrete contexts. And in this case, our context can be really efficiently represented as an integer. So when we create an abstract context, the context expression there, we basically make sure it becomes an integer. In this case, you can replace the whole by 0. So that would actually, a little simplification, you'll get k composed with 1 plus 0. And then you give away how you compose these contexts. In this case, you just add them together. So we can again simplify. And then finally, how you apply a context. And again, you can just add them together. So we get like k plus 0 and a little simplification more. And great success, we got like the standard textbook example of length, right? And this is all automatic and just reliably works. And you only have to, as a compiler writer, provide these 4 operations. And the same with reverse. I'll go a little quicker through it. Again, you would define like what context match. In this case, it would be left, right biased append. So you get you run the algorithm, you get again that same pattern. In this case, our contexts are lists of alpha. And when we create one, we use as a unit element the empty list. And then you can also define composition. It is just appending, except reversed arguments. We'll get back to that. Or applying a context. Again, reversed arguments. And then when we simplify the result, we actually get exactly the standard textbook example of reverse. Great, right? And this was actually described in 1986 by John Hughes. It was just a paper just about this instance, right? But now with our generic derivation, this kind of falls out automatically. Now we may be a bit worried, what if I accidentally do k1 plus k2 in the composition and it would be all wrong, right? And yeah, I didn't tell you something, you have to do a little more work. And it turns out you have to actually not do that much more work. You just have to prove that these 2 context laws hold for every instantiation. And usually that's quite easy. So one of them is, it says, if you apply over an abstract context, that would be the same as applying the original context directly. And that composition, abstract context composition, distributes over application. You can almost see the function composition right there, right? And you see the correspondence. And for example, for the concatenation one, the first law, you can kind of see that you have to do it like in reverse to make it hold. And more generally in the paper we show, for any right biased associative operators, this is all correct. So one instantiation is concatenation and lists, and you see that you have to apply them in reverse order. And then you can easily show these laws hold. And it's kind of funny because first I thought, we need commutativity because we switch the arguments. But it's really not the case. Associativity is enough because you're really associating towards the accumulator, and that's where the mirroring comes in. So this is very, very satisfactory. And when we were doing this, Anton came up with like many, he's a mathematician originally, he came up with many instantiations, right? And they're all in the paper and they're kind of fun to see. And I won't show all of them. I think one interesting one is the first one. So this says general evaluation context. So actually you can kind of match always and take the biggest context around a potentially tail-recursive call, and you can kind of represent that as functions. So you can create your abstract context just as a lambda expression over what still needs to be done, evaluation context. And then context composition becomes function composition. And context application becomes function application. That's very elegant. And now you just get the standard CPS conversion. So that's very, very nice, like one extreme case. But generally, you don't want to do it because you're really trading stack allocation with heap allocation. In most systems, right? Of course, if you're in Scheme, this already happens. So you're a happy person, and there it's really fast. So we show many more, like defunctionalized CPS. This gives you, if you apply to map, you would get the standard accumulating version of map that reverses in the end. We just saw the associative operators, left and right bias. There's monoids, semirings with multiplication and addition, exponents with like multiple function composition, product context like partition where you have multiple results. And this is kind of a higher order context because it would apply over multiple results over other contexts. So that's kind of nice. But a really important one is modulo cons. And that's what I'm going to look into more now, because that's the one where you can really get more efficiency in your program. And it's very common in functional programming. So modulo cons, what is it? Well, here's a map function in Koka. And I write it a little different so you can see more clearly what the evaluation order is. And then here you see this cons context, and it really means like any application of constructors where the first thing you need to do is the recursive call. And if you run our algorithm with these cons contexts, you would get again the same pattern as we already saw with the context composition. And I think now there's many things you could do. You could do the instantiation with the most general evaluation context, then you just get the CPS version, or the defunctionalized CPS one. But we really want a more efficient one. And people have been thinking about this for, well, exactly 50 years. But they realized if I start allocating these cons node and I don't yet put in the tail, I leave a hole there, I can in-place update it while I go through it. And that's the one we want, right? We want that efficiency. And this was actually exactly 50 years ago. Tore Risch in 1973 was writing about this with the REM-rec Lisp transformation. And then Friedman and Weiss, nice old style printouts of Lisp, and they give a more formal description. It's still very, it's more a description of an algorithm with the in-place update. There's no proof or something that it's correct. And then very recently, there's a really nice paper by Frédéric Boer, Basile Clement, and Gabriel Scherer. I don't know. Don't record this. It's a very nice paper, but again, it actually describes the tail modulo cons in OCaml in very much detail. And again, it's more a description of an algorithm. It's not immediately apparent that it's correct or why that would be the case. And also, it's not apparent. We have a very algebraic approach with context composition and application. How could we do in-place update in a nice way that connects these? Well, 25 years ago, Yoshihiko Minamide wrote a really nice paper at POPL about functional representation of data structures with a hole. And he uses something called Minamide tuples, well, what I call Minamide tuples. I think he called it just tuples. But and they're either empty, or the first element points to a big data structure, and the second element is a pointer to a hole in that data structure. So one thing you can do with it is apply such Minamide tuple to a final value. So you get you would get the Minamide tuple here, and it points to a big data structure with a pointer into the hole in that data structure. And then you can just plug in a value, and then you get a final result. And this is very efficient, just pointer assignment. And the other thing you can do is you can compose these two Minamide tuples, and you get a new one back, where you basically, the result structure pointer stays the same, and you just keep the whole of the second structure. And now you can build bigger structures by composing them. And this sounds almost like we want. So let's look at that. Here's the map again. So our algorithm, we say, any sequence of constructors will match. So we rewrite it in this common form. And now we're going to say, well, what are our contexts? Well, Minamide tuples. Great. So it will be like, I don't know, some value plus a pointer into it. And it's clearly an internal compiler representation that you don't want to expose to the user. So for example, when you create a an actual abstract context from a context with a whole, you actually just create a value, but you keep the address of the whole in that value. It would be like first represented by a null pointer or something. So I denote it like this. So we can simplify the program a little bit with the thing we're actually creating. And then it turns out that context composition is exactly Minamide's whole composition. And context application is exactly Minamide's whole application. And I found it really nice to see. There's like this 25-year-old paper, and we didn't have to change anything. It was just right. So that gave me a very fuzzy feeling. Again, great success. And we can actually prove it really nicely. We can use the operational semantics of Minamide just, as they are. You can just do nice equational reasoning. And you can show that the context laws actually hold. So that is very warm and fuzzy. And I give a little bit, when you compile this, it's actually going to be very efficient. So I give you an example of one execution. Like this K here will be some partially built data structure now as a Minamide tuple. So it will look a bit like this. It's partially done, but we still have to provide what the tail will actually be. And then we compose it with our new thing we're generating, in this case just one cons, which is also a little Minamide tuple. And then we compose them, it's like constant time you assign, right? So now you get, again, a bigger list, and you still have to provide the final value. And this can be really, really efficient, right? And it's really important. So what drove this work, I wasn't actually interested so much in principle in TRMc, but we were working on trying to do FBIP algorithms, Anton and I, for example, which we call functional but-in-place algorithms. And we had this quote in earlier papers that says, just like tail call optimization lets you write loops in a functional style, reuse analysis, which comes from the Perceus reference counting, lets you write in-place mutating algorithms in a purely functional way. But it really is, it's kind of wrong. It should really have been reuse analysis with tail-recursion modulo context lets you do this. And you can kind of see that when you see the map function. You kind of want to write the obvious functional version, like this, so that the reuse analysis of Perceus sees the obvious connection between what consel can be reused. So when you actually execute this now, and access happens to be a uniquely owned list at runtime, then you will in-place update the head field with the result of fx, and then you will leave a little hole in the reused consel and go to the next and the next and keep updating in place until you get to the end, and then you return the list. So you're really doing what a C programmer would do. And this gives really good efficiency. The only extra overhead that's still there is that we keep assigning the tail field, which is going to be the same pointer as we're actually having, because we are reusing every consel. But it could be that like the end of the list is maybe shared, and then copying will happen dynamically. So that's a difficult one to actually optimize further without more static guarantees. But this is good stuff. Right. Of course, the audience would have asked me already, how can this be saved, this Minamide stuff, update in place? Of course not, right? So Minamide actually gave a linear type system to ensure you use these tuples in a linear way. And we can actually prove that the way our algorithm generates the code is actually safe. So we do this in the paper. And we show it even more precisely with the linear resource calculus, partly done by Ning Xia here, where we give a beautiful proof of why this is okay, and also characterize precisely why in-place update is okay if you have unique references. So if you love proving stuff, this is I would encourage you to read the paper. Unfortunately, it sometimes breaks, and especially in Koka. And that is if you have nonlinear control flow. And you can actually easily see this if you have our map function that we optimized, and suppose the call here, fx, would actually return more than once. And this can happen with general algebraic effects, like in Koka. And we want it, because we want to do probabilistic programming and stuff. But also if you have call CC, you could easily resume twice or shift reset, etc. It won't happen if you promise to always resume at most once. So this is in OCaml 5, the one-shot resumptions, you'll be fine there. But if not, the update will kind of happen twice because you've captured the Minamide tuple that's k in a non-linear lambda, and now things can go all wrong, right? And actually, first I was like, oh, I have no idea how to really prevent this. But we came up with a really, really nice solution. I have almost no time to actually show you that. Maybe read the paper for a really nice solution. But if you have reference counting, you can kind of, when you create the linear chain that in the context path, basically, you can actually keep track of which pointers lead eventually to the hole. It will always be a linear path to the hole. And you can while you create the constructors, you can keep track of that. And then you can make dynamic copies at runtime. And Gabriel Scheer had a great observation that you don't even need reference counting for this. You could just look at the hole if it's actually already written with a specific value or not, and then copy dynamically or not. So that's a very good solution, and it works great in practice. So, but yeah, see the paper for details. I just wanted to show you a bit of the benchmarks. So here's map, each time mapping over differently sized lists, but always a total of like 1 billion elements. And the first bars are red, that's us, with tail-recursion modulo cons, and then the second bar is the standard version, if you wouldn't do it. And then you see, for example, if the lists become big, the standard version runs out of stack, but the TRMc version keeps working. And you also see, and this is kind of important, when the list is really small, like one element, we're as fast as the small list. And this is not always the case. In OCaml, there was some trouble with that. But the nice thing is, if it is like this, we can always apply the optimization. We don't have to, it's always better to do it. And you can also see that everything's normalized against TRMc. It's always faster than anything else. So you can't manually get better than this. But it's also a good property. And it also works if only part of your calls are tail-recursive, like in red-black tree insertion, where there's sometimes very big improvements possible. Read the paper to see 1 minute. Right. I think an interesting thing in the OCaml tail-recursion modulo cons, they use something else. They use destination passing style. It kind of looks like this, where you kind of get two copies of the code. And I was like, this is how does this relate to the Minamide tuples? But now I kind of see it. The first time a Minamide tuple is always empty. That's kind of the code we see here on the left. But then it switches because now we know the result. We can store the result something. We know the destination. And now we just iterate to the rest of the list where we update the destination. And that's really saying, like, once you create the initial Minamide tuple, the result will pointer always the same. So you could just, just iterate through the second part. And that's what's happening here. So it's really a kind of an unrolling of the Minamide tuple code here. And that was it. Hope you enjoy it. And time for questions. Right.
Okay, so we have about 3 minutes for questions. Raise your hand high and our intrepid SVs will come around and bring you the mic. And when you get the mic, please say your name and your affiliation if you have one.
Hi, I'm Neil Krishnaswamy from the University of Cambridge. One question I had was, you said that you could do CPS translation as well by making everything a context. So I wondered if you could use this to implement delimited control as well by having something that marks the end of the pattern for the context matching.
That's a great observation. I don't think so, because when I said that CPS, I was kind of lying because I only do self-recursive calls here, right? Or mutual recursive groups, not general CPS conversion where any tail call would be done. So you would have more had to be done. But maybe this can inspire people to find that, right? Yeah.
Hi.
Um,
Jacob Waitman, Risk Zero. For a Koka programmer trying to, understand the performance characteristics of their program, are there any pitfalls to be aware of with this? I appreciate you touching on effects and reference counting in the talk. Is there anything else to be aware of when using these with this optimization?
More has to be done in the Koka language specifically, right? Language design wise. So this paper doesn't touch upon it. But one thing we definitely want to add is say like a tail keyword that you can add to your function. So you now, if it happens to be not actually that your context is slightly wrong, you would actually get a warning that there's no optimization happening, right? So we definitely want to add those kind of warnings. It is different though than OCaml that we will always try to do it. And that's because our performance seems to be always better, right? So it's always a good thing, but I would love to give more guarantees. With the reference counting stuff, I can't talk about it yet, but we can talk about it offline. And also with Anton Lorenzen, if he's here. Right?
Yeah. Is this available today in Koka? Is this implemented in Koka yet?
Yes, no, this is these are real benchmarks. We really need it. Yes.
Thanks.
Okay, I think we have to move along to the next talk, unfortunately. Let's thank Daan again.